Hello, everybody, and welcome to this presentation on GitOps with Kubernetes. This presentation was given on the 28th of January at the TechTrain event in Mechelen at Kronos. And for your convenience, I'm recording it here a second time so that you can pick up whatever you'd like to pick up from it. Let's get started. What we look at today is, first of all, what is GitOps? We'll explain what it is and what it is not. We'll contrast it with traditional CI ops, or just call it your traditional CI CD systems. And then to get GitOps to work, we have to have some additional software installed. They're GitOps operators, and we'll take a look at the ones currently on the market, which ones are interesting, and then we'll focus a little bit on GitOps with WeaveWorks Flux. Now, this is an introductory post or introductory presentation. We won't look at advanced, very advanced scenarios. That's maybe for some other time. Now, of course, we're talking about Kubernetes and GitOps on Kubernetes. So these two aspects, of course, are really important. Kubernetes, let's say the de facto open source container orchestrator, where it's always the same thing. You define your desired state in a file, typically a YAML file. You submit that desired state to some API server, and then the API server or systems software within Kubernetes is going to apply the state that you desired to the cluster. So that lends itself extremely well when you hear about configuration files. That lends itself extremely well to storing them all in Git in a version control system, and to use the properties of Git like check-ins, pull requests, and so on to control your Kubernetes configuration. But clearly, just having Kubernetes and Git is not enough to do GitOps. Probably today everybody is storing some sort of configuration files in Git. To truly do GitOps, there are some other properties you have to think about. Now, why do we do GitOps on Kubernetes, and why is Kubernetes so useful in this case? Well, it's all about this, but I just really explained it already a little bit. It has to do with the fact that continuously there is software running in Kubernetes which looks at the actual state, then fetches a desired state, and then tries to match the actual state to the desired state. And that's continuously going on in a reconciliation loop, and there are multiple of such loops running within Kubernetes. So it's a desired state system, and of course, if we can express our desired state fully by configuration files in a Git repository, that's a property that is useful towards this GitOps approach. And of course, the actual desired state, you're going to do this or reflect this in YAML files. You see a very simple YAML file in front of you, which is just a deployment, in this case of a Redis container. Nothing too fancy here. Basically, it will be a bunch of YAML files that you apply to your cluster. So that's one thing. This desired state that you have to define, and that is continuously running reconciliation loops. That means that with Kubernetes, it's the ideal system to work declaratively versus imperatively. And what does that mean? With imperative management, it's clear you run commands either yourself interactively or scripted. You create a bash script or other kinds of scripts, and then you run them yourself, or you let them be run by another external system. Or you have a declarative state. You declare the desired state, and a backend system sets the state. And in this case, we'll use Git to save our desired state. We'll have some GitOps software that sets that desired state on Kubernetes, and then Kubernetes does its thing with its reconciliation loops and make sure the desired state is implemented. And that's what GitOps really is all about. It's declarative, fully data-driven management of your applications in Kubernetes. Now, if you look a bit closer, GitOps is merely a method of continuous deployment. Yeah, so it doesn't replace all the tools you use today to do your development, create your images, and so forth. No, you're going to still use your CI systems. Your developers are still going to use those systems. You're going to do tests. You're going to do the building of your artifacts, your containers, your Helm charts, and so on. That's all done in a CI system. But then, of course, the actual deployment of the artifacts that you build, yeah, that's then handled by GitOps, by a GitOps approach, by GitOps software. Yeah. And of course, Git in this case is a single source of truth for declarative infrastructure and application. What does that mean? Yeah, all your configurations, the entire configuration of your cluster, your applications, and so on, is stored in Git. And you use the Git properties like revisions, change control, rollback, and so on as part of managing the cluster state. Yeah. So we'll see later if you have a GitOps operator or GitOps software installed, yeah, they won't give you the option to do, let's say, rollback or have change control mechanisms, because that should be handled by Git. So Git and the GitOps software that you install will work together. An important aspect of GitOps is that it is a pull-based approach. So you have some software running in your cluster. That software is responsible for looking at the Git repository. When it sees some changes, it pulls in those changes and applies them. So there's no need to provide cluster credentials to an external system like with a traditional CI/CD system. That's not required in this case. Yeah. So if you think about it, GitOps, in short, a fully declarative, data-driven, pull-based approach to how you do continuous deployment. And if you compare that with CIOps, if you want to call it that way, or traditional CI/CD, yeah, that's typically pipeline driven, right? So Azure DevOps is doing such things, other systems as well, and they're steps that execute tasks. And it's not uncommon that a task is a bash script task, for instance, and there's a bash script somewhere in there that does all kinds of configurations. Yeah? And then you're working more in an imperative way, which is not what you want to do in a GitOps world. And of course, you have to supply to these systems, you have to supply credentials to one or more of your clusters. Okay, I'm not saying that's let's say a favorite attack vector to get into your system, but it is an additional attack vector there. And of course, this one is more push-based. There's nothing running in your cluster. The external system pushes the changes to Kubernetes in this case. Now, it's not an either-or situation here. What you get is the fact that you'll use these two types of systems together. As I said earlier, you will still do traditional CI even in a GitOps world, because you have to build your containers and your artifacts in some way. But you'll combine it, or you could combine it with GitOps to actually take over the deployment steps, if you really want to work fully declaratively and fully in a data-driven fashion. And of course, in a pipeline-driven approach, in a CIOps approach, you typically have configurations like this. This is just a view on the execution of a pipeline. The pipeline itself is also a YAML file that defines all the steps, but you typically have some graphical user interface that gives you a nice overview of the steps. Did they succeed or not, with full logging, etc. So of course, these are nice systems. These are well-established systems. There's nothing really wrong with these systems. It's just a decision. Are you going to use GitOps for deployment, or are you going to use the release pipelines in a traditional CI/CD system to release your software? That's a bit up to you when you compare how these two systems work together. Now, let's have a small demo. It's not really a demo, but I'm going to show you my Git repository, the one that we will apply to our cluster. And you see that here, this is a public repo, so demo clue Flux. If you go to github.com/gbake, you'll find it there. Now, there's nothing really special here. The thing is that I just put my configuration, so the config that I want my GitOps software to apply to my cluster is in the config folder. So in some shape or form, when I install my GitOps software, I will have to point to this configuration folder so that the software knows, okay, I have to apply everything which is in there. And that's basically what the software will do. It will take all the files in there, all the YAMLs which are found in subfolders or directly in that folder, and it will apply them to the cluster on a continuous basis. For example, every minute or every 5 minutes, it will go to this Git repo and do something with it. The main application is here. It's the real-time application, which is nothing more than a sample, right? It's a sample that contains a deployment which is Redis. It's a Redis backend, and then you have a small application which is a web frontend written in Go, using some kind of library to do WebSockets. And this application is monitoring a Redis channel, and when there's something appearing in the Redis channel, it will just display what is appearing there on the screen. Nothing more than that. But what you see here already is that, of course, the image I'm using, that's Gebaka Flux app 1.9.9. Excuse me. You also see that there are some special annotations already. I'll explain later what they are, but that's a way of the GitOps software that we will use, the Flux software, to control releases to this piece of software. So normally, this is running already, I think. So I will go to real.baka.info. I will check if it runs. Yes, it runs. And there's some kind of system that also puts some kind of demo value to Redis. You can see that here. If you go to the YAML files and you go in the real-time folder, there's a small Redis client here based on the following image, and there's a small script in there that says, you know what, forever with a sleep 1 second, please publish something to that Redis channel called device01. And this one here is just listening to publishes to that channel, and it's just responding there with that. Nothing more than that. Very, very simple. Excuse me. Now, that's it. So we want to apply the configuration of that Git repository to our cluster. Now, we have to install a piece of software here. So it's not enough to just have Kubernetes and then to have Git and then maybe to run some commands to apply everything which is in that folder. No, you need to install some additional software, and that will be a GitOps operator. Now, if you take a step back, an operator, controller, what is that? A controller in Kubernetes is responsible for a specific resource type, right? So if you create a deployment, there's a deployment controller, and that one is implementing basically what you asked the deployment to do. And lots of times these controllers delegate work to other controllers. And so if you create a deployment, it delegates work to a replica set controller, which creates a replica set. The replica set controller delegates work to a pod controller, which creates a pod. Now, an operator is basically an application-specific controller. That's something you can even write yourself, or that many others have already written for you. So you find GitOps operators, Helm operators, a Prometheus operator. You'll find MySQL operator, which installs MySQL for you, and so on. And basically, if you go to operatorhub.io, and I'll just go there, so operatorhub.io, you'll find a bunch of operators that you can actually install within your cluster, and all kinds of famous or well-known software is in there. You see an operator to install an AK cluster provided by the folks of at Lightbend. An API operator. You find AWS S3 operators. You'll find a lot of operators available today already, which are basically application-specific things. For example, one that installs MongoDB in your cluster in the proper way, also an operator, right? Now, of course, we could actually write the operators ourselves. It's not terribly complicated, depending on the framework that you use. And to actually build your own GitOps operator wouldn't be that difficult. A simple one wouldn't be that difficult, because you basically have to go to a Git repository, pull all the files, and apply all the YAMLs. That's what a very simple GitOps operator could do. And you could use the operator framework, which is a Go framework, or easier to use the framework, Python framework, COP, which was made by Zalando. Yes, right, Zalando, which is quite simple to do. And if you go to my my blog, sorry, shameless plug here, but it's my channel, so I do what I want. You'll find actually one of the latest posts of if you search for it here in the search bar with COP, you'll find a post on how to write a simple Kubernetes operator with COP. So I suggest you check that out to see how an operator works. But clearly, we're not going to write our own GitOps operator. We will use one which is available and written by others who can do it, well, certainly much better than I can write it, right? So let's take a look at the GitOps operators which are available on the market today. Well, basically there are two. You have Flux, and that's the logo at the bottom left. That's the WeaveWorks logo. WeaveWorks is a commercial company. They also have a commercial product, which is called WeaveWorks Cloud, which is also doing GitOps for you, among other things. And they created the open source Flux software. Then the cute icon at the top there is the Argo icon, also a GitOps operator with some different feature sets, similar possibilities, but a different feature set. At the moment, these two projects are actually working together, have some kind of initiative to actually improve the software or learn from each other or implement features from the other in their own software and so forth. So there's some movement in that space as well to have additional and more robust features. Now these GitOps operators, so we have to install them. In a moment we'll see how it's done. They're continuously running. So they typically check every minute or every 5 minutes. They check your Git repo. Why is it not fully webhook based? Well, that's typically not a good idea, because if you only would apply the changes to the cluster when you do a change in your GitHub repo, you can't repair change state that somebody does to your cluster. So, for example, if you're applying the real-time application that I've shown you earlier, the real-time application is applied from GitOps, from a Git repo to our cluster, and somebody imperatively is changing the image version or is modifying the application in some shape or form, which is not supposed to happen, then the next interval, the GitOps operator will make sure that the state that you have declared in your Git repo will again be applied to the cluster. So that's the reason why you do it that way. Now you can configure webhooks additionally to let the software trigger an update faster, but that's something that you will need to do yourself or configure in the software. Now we look at WeaveWorks Flux, the basics only, which is of course a GitOps operator created in 2016, and that's a CNCF sandbox project as of August 2019. So as you can see, a developer is still working on his code base with a version control system, and then a CI system is basically creating the artifacts, creating the containers. Then you push the images to a container registry, and besides that, you have a config repo for the GitOps software to implement your Kubernetes state. And as you'll see later, those two together, so the container registry and the config repo, can be used together to also update your applications and do continuous deployments. But that's something we'll look at in a moment. Now you might be wondering, okay, it's a sandbox project, it's maybe not that widely used yet, and so forth and so forth. Well, actually, if you look back a little bit at the Ignite conference where Microsoft announced Azure Arc and Azure Arc for Kubernetes, they were actually using WeaveWorks Flux to keep their clusters, multiple clusters, which were under the control of Azure Arc, up to date. And that's basically a great use case if you have clusters deployed in the field, or maybe more and more in an edge scenario where you need to reliably run software at the edge, and you want to use Kubernetes for that, for example with multiple Azure Stack Edge appliances. Then of course GitOps makes it, I think, much easier than traditional approaches to make sure that a shared configuration is dropped on those clusters. So you'll see how that evolves. Azure Arc is for Kubernetes is still in a private preview, and we'll see how they use the software, and Flux, how they use that further, because it was nice to see that they indeed were using the software already, and that this GitOps approach is coming to the bigger vendors as well. And I believe AWS is also working on that together with WeaveWorks and so on to make this more a reality in that cloud as well. Right? So it's gaining traction. So it's good for you to look at it and see, is it going to fit in my scenarios. Now the Flux installation is very simple. I'm not going to go very deep in that. You can install it with flux_ctl, which is a command line you can just download and install on your system. You can install it on Mac. You can install it on anything you want basically. Not on Windows, I think. Or you can install with a Helm chart, and in this case this is a Helm chart deployed by Azure DevOps, just to give you that is possible as well. And here you see I'm installing the Helm chart for Flux, and I'm overriding some values in the Helm chart. So the Git URL, of course, is important to be set. I have to set it to my Git repo. I also change the poll interval here, and I will also have to change the path to use the config folder, right? So that's an important one that we have to do. Oops, sorry. Now, of course, you have to link your Git repo. We do that during the installation of Flux. We point to a repo during the installation. Then we configure a deploy key, an SSH deploy key, for read-write access by Flux to your Git repo. How do you do that? Well, there's a tool, or the flux_ctl command line has an option to retrieve the identity, which would just be the public key of the SSH key pair that's automatically generated by Flux upon installation. And by the way, you can supply your own key pair if you would want that. If you don't, Flux will generate a key pair for you. So you retrieve that public key from the key pair, and then you set that key as the deploy key on your Git repo, in this case on GitHub, as you'll see in a moment. So let's take a look on how we can actually do this. So I have my Azure Cloud Shell ready, and I'll just see if my cluster is operational. So let's look at the nodes of that cluster. And after that, I will show you how to install the actual pieces of software. That's coming in a moment. So yeah, there we have them. They are ready. Let's see, I have a small script, and that is the script to install Flux. Yeah, it's just a Helm chart installation. So there you can see we create a namespace, we do a Helm upgrade with install option, that's okay. And there you see the Git URL is set to my gbake demo clue flux URL. Poll interval is set to 1 minute, and the path is set to the config folder. That's all there is to it. I don't have to install because I actually already installed it, but then I would just run this script and it would be installed. So that's great. Later we'll also need a Helm operator. I'll explain later why that is. The Helm operator is also in there. So if you do install and then the Helm operator, you'll see that the Helm operator is using a custom resource definition, a Helm release custom resource definition. So that's first applied here, and then we install the Helm operator with this command here. We specify some extra values to get this to work. So if you're looking at the namespaces, you'll see that there's a namespace which is Flux CD. So let's switch to that namespace and then get all the pods running in that namespace. And there you see Flux, the operator itself is running already a while. Yeah, Flux is using a memcache in the backend to store some data. That's fine. That's automatically installed by by Flux, and you could use your own instance of Memcache if you want. And then, as you have seen, we install a Helm operator as well. Explain later what it does. That Helm operator is also installed in that thing. So if you do a kget crd, so all the custom resource definitions which have been installed in the cluster, yeah, Argo is also running in this cluster. But for example, you can see here that you have the Helm releases.helm.fluxcd.io custom resource definition, and that will allow us to create Helm releases. That those ones will then be acted upon by this Helm operator. So that's what we're going to look at later. Yeah. So installation is fairly easy. Of course, yeah, I forgot to do something. That's indeed true. Let's do fluxctl identity. Yeah. That gives me, as I explained earlier, the SSH key or the public key of the SSH key pair. I will have to give it the namespace, which is flux cd. Yeah, so let's take a look at that key. That's the one. Let me just copy that key here. Let's go to my repository in the settings, and there you'll find deploy keys. Let's delete this one. We add the deploy key here, so demo key. We paste the key in here, and we also allow a write access. And we give, in this case, we give the Flux operator, the GitOps operator, the possibility to actually write back to your Git repository. That's an optional thing, but it can be quite useful, especially when you do image management and application updates. And you'll probably have seen already, if you look at my Git repo, that and I'm going to the code here. You see that here, for example, WeaveWorks actually has done something in the past. Yeah, it released application version 1.9.9. So he went into this Git repository and changed something. What did he change? Well, he actually set, upon the availability of a new image, he actually set in the real-time YAML, the following was modified. He actually put this here, fluxapp 1.9.9 is actually was actually set. We can take a look at the history maybe, and there you can see it. There you have auto release Hibaka fluxapp 1.9.9. Yeah. Yeah, so that's actually the one that was being that was being changed, right? So we did that now. So we configured, we installed the Flux operator, which is a very simple thing to do, and then we made sure that it has access to our Git repository. Now it's important to note that one installation of Flux can only use one repository. That doesn't mean you can't have like multiple repositories as a source for your configuration. For example, you could have multiple namespaces or whatnot, deploy multiple instances of Flux, and then have each instance of Flux use its own Git repository. That is possible, but I'm not doing that in this demo. I'm just doing one installation of Flux, and that is using then one Git repo for the entire cluster. Yeah, that's just how it's done here in the demo. Now this is great and easy. Yeah? So you now know, well, that's very simple. Just have my YAML files in Git, deploy simply this Flux GitOps operator, do the deploy key, and it's done. Yeah, sure, that's right. But then there are all kinds of things you have to watch out for in a GitOps world. You'll have to do this a little bit differently than in your traditional CI ops world. And for instance, deploying a Helm chart, yeah, that's normally done with a tool called Helm, and you run Helm upgrade and things like that. That's not something you can do now because you're working fully declaratively in a data-driven approach. What you can do, and that you've seen me do earlier in a demo, you can install something which is called the Helm operator. And the guys from WeaveWorks, they have a Helm operator as well. That's the one that I installed. Now, what the Helm operator does is nothing more than, first of all, defining a custom resource of kind Helm release that you see here on the screen. Then you can just create YAML files that look like the one you see here. And in that YAML file, you can, for example, set the chart to install, the values to install, and all other kinds of options which are relevant to the Helm operator. So then you can work fully declaratively with Helm charts. Very simple to install a Helm chart. You just use those kind of files. That's the reason that here in my config folder, you'll find the Helm folder, and there you have a demo chart. I just installed a demo chart here, and I use indeed a custom resource of type Helm release. And there I'm saying, well, actually, I want to use the InfluxDB chart from the repository by Bitnami, and that's the version. And I'm not setting anything special here. I'm just saying install the default chart. But of course, I could set the values and other things to install the chart as I would like to do. And by just having this in your Git repo, the GitOps operator can actually apply it to your cluster, and then the Helm operator kicks in to do the Helm install or the Helm upgrade for you. Yeah, it's as easy as that, right? So that's one thing. Deploying Helm charts, you'll have to install some additional software for that to get it to work. Second thing is, of course, how you deal with secrets. In a traditional CI/CD system, I can, if I want to, I can put my secrets in there. I would typically integrate with something like Key Vault or something like that. But there you have those kind of options. In this case, when Git is your single source of truth, you don't want to put plain secrets, certainly not in your Git repository. So how do you do that? Well, of course, the first option is that your application should retrieve the secrets. The application code that you write, make sure that the developer is using some kind of vaulting system, and he retrieves the secrets from the vault, secret certificates, whatnot. Of course, you don't have access to your source code all the time. Sometimes you have to configure software yourself. And then there are again several options. First option, for example, is to use the sealed secrets operator. And the sealed secrets operator by Bitnami allows you to create, again, a custom resource. That custom resource, just a YAML file that you use for that, contains an encrypted secret, encrypted by public private key cryptography. And that means that those sealed secrets with that encrypted secret can be put in your Git repo. When your GitOps software is applying that sealed secret to your cluster, the sealed secret operator is kicking into gear, and it will actually use the private key to decrypt the sealed secret and turn it into a regular Kubernetes secret. So if you wanted to, you could just use this sealed secrets operator and then put all these sealed secrets in your Git repo. And there are other ways of doing it as well. Or there's also something which is called like secret injection. There are many tools available for that indirectly inject the secrets in the pod, either in the file system or as an environment variable directly. So there's all kinds of options available. I have worked with this one a couple of times, which is a very easy one to use, and that's the Azure Key Vault to Kubernetes controller, so to speak. You'll find it at that URL. And again, that's a custom resource definition to allow you to create Azure Key Vault secret resources. And here you see, if you take a look here, here you see that in the specification I point to a vault called Geba Key Vault in my Azure Azure subscription. I'm telling the software, please take the event endpoint secret from Azure Key Vault, and the output should be a normal Kubernetes secret that you would normally create yourself. Of course, then in that case, the secret will be base 64 encoded, that you know by default with secrets, simple base 64 encoding. So having files like this in your Git repo is enough to pull the secrets from Key Vault and to then actually create custom or standard secrets in Kubernetes. And I'm using that here in the, if you look at the config file, if you go to the KEDA folder, there's a function which is actually an Azure function that was deployed, and that Azure function requires the connectivity information to an event hub, but also to a storage account, and those are sensitive values. So what I'm doing first is I store these values in Azure Key Vault, and with this configuration, with these Azure Key Vault secrets, I'm telling him, please pick up the event endpoint, also pick up the Azure Web Job storage secret, which is a link to my storage account, and make that into regular standard secrets on my cluster. Then in my KEDA configuration, in my IoT function that has to connect to the event hub, I can simply refer to it with environment variables. Event endpoint is an environment variable, as you can see here, and the value of the environment variable, we use the value from system to actually retrieve it from a secret key. That's the only thing that we are doing here. Yeah. If you look in my cluster, and I think that's, I don't know what namespace that is. I think it's the default namespace. So KNS default. I will take a look at the secrets. So we'll do a get secret. And as you see there, you have the KEDA sample event and KEDA sample storage. So get secret KEDA sample event, and give me the YAML completely. So then there you will see, and I mistyped it, secrete, that's not the one that I want. So give it, let's modify that. And there you see the event endpoint, and that's actually the one, that's the event endpoint, but it's base 64 encoded. So I could take this value and I could use the base 64 command line and decode it and blah 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 to see the actual value. And so that's how typically how Kubernetes secrets work. But these secrets were created by this operator from Azure Key Vault. So that's one way of dealing with secrets in a GitOps world. The GitOps operators themselves, they don't really have a preference on how you use it. So if you want to use this one or something else, they don't really care. Just use what you are comfortable with. And a last thing, which is quite an important one as well, is, yeah, we're saying it's a CD system, continuous deployment. That's great, but how do you do that? Do you just have to modify your YAML files in some way and then let the operator deploy it? Or is there some additional feature set here at play? And Flux indeed has additional features, has the concept of workloads. A workload is basically any cluster resource that creates images, or sorry, that creates containers from versioned images. So that's a deployment, a daemon set, and so forth. So if you use Flux CTL list workloads, you'll see all the workloads in your system that adhere to that. So let's take a look and see how that works. So if I'm clearing this out, and I'm doing Flux CTL and then list workloads. Yes, should have set the forwarding namespace, but we'll just do it like this now. That's okay. We're not going to continuously use these commands. Okay, I can't type. So there we have it. So we have all the workloads running on this cluster, and as you can see, it gives me some information about all of this. And one of them is automated, and indeed the image is set to 1.9.9. So okay, you can list the workloads. That's fine, but you can also update a workload to a new image. And you can either do this imperatively, and you can say, for instance, I'm doing Flux CTL release, as you can see in the bottom there. You specify the workload, and then you specify the new image that you'd like to use, in that application. That's fine, but actually, it's if you want to do this in an automated way, you can set that in the YAML files. And you've seen that earlier when I said you see something already in the annotations. When you annotate your deployment, for instance, or your daemon set, it doesn't really matter, with these annotations. In this case is an example. We set automated to true, and we also have said, look, the tag in for our real-time app, we'll use a semantic versioning filter, and everything which is major version 1, if there's something like 1.1.1 or 1.10.10, whatever, you're going to automatically deploy that. You're going to automatically do this for us. That also means that Flux is scanning images in your repository. So in my case, that's just on Docker Hub. It can also work with ACR and so forth. That's all possible. But indeed, it has to scan the images in my repository to see, is there a new version available? When there's a new version available in the repository and it matches the annotation, it matches my filter, in this case, the semantic versioning filter, then he can actually automatically update the image based on that spec. And as you have seen earlier already, Flux will write this as well to your YAML file, in order that the YAML reflects the real state. What is the current version being deployed to your cluster? And you saw that in my Git repo. That's 1.9.9 was actually being deployed, right? So that's how you automate releases. Yeah, sorry. But one last thing, maybe garbage collection. That's not turned on by default. What does that do if you turn it on? Well, if you then in your Git repo remove YAML files, you remove resources, they can be removed in your cluster as well. But by default, that's not the case. So if you start playing with it and you remove stuff from your Git repo, don't expect that the actual state on your cluster will change. You would have to turn on garbage collection as well, and that's done during installation. One of the values in your Helm chart, for instance, there you can actually turn on garbage collection. Yeah. Yeah, I'm not going to do a demo on the image updating. That's something which you can find elsewhere on my YouTube channel on how to do that. But let's actually end with this here, with environment management, because that's also something you have to think about here. In a traditional CI/CD system, you normally have the possibility to say, well, this is the deployment for the environment, dev environment, this is for Q&A, this is for production, and you can create these flows quite easily. In a GitOps scenario, how do you do that? How do you specify what the system needs to do in dev and what the system needs to do in, for example, production? Well, you can fill a whole book with that, but let's say common approaches would be to put every environment in a Kubernetes namespace in the same cluster. I would use a single branch for all environments and have everything together, and then use something like a customizer that customizes a deployment for each environment. And these tools like Argo, but also Flux, they support several of these tools that can do this. And let's say commonly used tool is the customize tooling. So Flux has support for customize. With customize, you would specify a base folder that's the same for all your environments, so you don't have to duplicate that per environment. That's already a great saving. And then you would have some kind of like overlay folders per environment with customizations. So in this case, we have a dev and a prod environment. Dev and prod all go to their own custom namespace, and then we let Flux also patch these environments to have some differences. For example, I have used Flux in this case. In dev, I'm doing an automatic update of the image all the time. In prod, I don't do automatic updates. Somebody would have to modify the YAML file with the version of the new container image to be used, and only then will the prod update be done. That's just an example. I'm not saying you have to do it that way. So if you look at how the customize system then actually works, we can go again. I have an example in the config folder. There you'll find, sorry, not in the config folder, in the customize folder in my repository, and there you'll find the base. I'm not going to go in there. That's just my base configuration files. Then in dev, you'll find that we said in the standard customize file, customization.yaml. There we're saying, okay, if you're doing this environment, you'll have to, on top of the base, also execute or apply this resource, the namespace.yaml file. And when you're doing deployments, use the namespace real-time dev, right? And of course, when you have applied this namespace, make sure you also do the base. So if you're looking at the namespace, indeed, we are creating a namespace called real-time dev for the dev environment. And in the prod environment, that's similar. There we have namespace PRD for the production environment. And then, of course, if you go to the dev environment, there I said I would like to patch the base files, which just say how to deploy the application. I would like to patch them, and Flux will do this with some changes. So how can Flux know what to do? Well, there's a .flux YAML in the folder. When there's a .flux YAML in the folder, it knows, oh, I have to run customize on this with this folder. And there's a patch file that I run on top of customize to modify it. So if you then go to this flux.patch.yaml, what you see there is that I'm saying, you know what, the deployment we're going to do, well, that deployment, you should actually, first of all, put these annotations in there, and also in the template, modify something. We will actually set the containers that we want to use. So that's an important one that you do. And also in this case, I'm saying, yeah, in the dev environment, the ingress should use an ingress URL. It should use real-time dev dot something else, or real dev.backer.info. In production, I will use a production URL. So that's also something you can do and modify your ingresses there for each environment. Yeah, this is just a basic customize file. Also, be aware that you'll have to do something specific during the installation as well of your Flux software. You have to do something additional to get customize to work. I refer to the documentation for that. Suffice it to say that for me it wouldn't be enough to just put these customized files in the config folder and it would be magically applied. So there is some additional work to be done to work with environments. But again, take a look at the documentation to see how that actually works. So we've come to the end of the presentation. So you've seen how to drive deployments from a Git repo. It's a fully declarative, data-driven, pull-based approach, and that's basically what GitOps is. No imperative management, fully data-driven, and it's pulling the configuration to your clusters. You don't have an external system that pushes the configuration to your clusters. It requires new tooling, like Flux or Argo, or maybe later combinations of those, or new features created by both of them. We'll see how that works. But you'll still use this in combination with your existing tools for secrets and environment management and so forth. And it's clear, logically, it does not eliminate the need for CI or tools like Azure DevOps or Jenkins. You'll use these two together. And if you're comfortable with the GitOps way of working, then you will replace your continuous deployment with the GitOps way of working. And that's typically how you then do it. You combine the two tools together. Good. I hope you like this. A bit of a shortened version of the demonstration or the presentation I gave at the TechTrain Mechelen on the 28th of January 2020. If you have questions, just leave them in the comments, and till some later time. Bye bye.